That was really fast. That was super fast. Incredible. Ah. Ah. Oh, Gath! Gath is here. Everybody. Gath is here. Oh no. Oh no. Oh no. No, no, no. No. Ah. Oh no. Hey, is there something wrong with Discord? My, something's weird going on. I don't know. Okay. All right. Good. Okay. Yeah, is that something weird's happening with Discord, huh, Crow? Like I type stuff, and it shows up red. And then wait, it didn't show, it went away. What? Discord is not working? Oh, okay. Okay, got it. Okay. So, students. I guess I shouldn't look on Discord because it's messed up. But maybe I should look at... Oh, 9 of you are here. That means my students are here, ready. Okay, here we go. Here we go. Today's class is 3 parts, as usual. My 3-part scheme. Class, there will be homework this week. I'll figure it out one day. And so just be on the lookout for that. It'll be on chapters 13, 14, 15, smattering, because that's what you should be reading. All right. So today I'll talk about 3 things. First off, hello everybody. Come on in, have a seat. First off, I should say that in this class, this semester and the continuation next semester, our focus will primarily be on commutative rings. Those are rings where the multiplication rule is commutative. So, not, matrix rings, those are cool and all, and it's good to test definitions against them, general definitions, but please understand that our focus will be primarily on commutative rings. Okay, and that's what I'm going to sort of assume that we're working with when during this lecture. Okay, so the first thing I need to tell you is what an ideal is. What is an ideal? And then maybe some examples. And then examples. And then why? Why is an ideal? I'll try to give you part 1. Okay. I'll give you my first BS mumbling about that. Okay? Second thing. We'll notice that there are some really easy ideals one can write down in this world. They're called principal ideals. And then part 3 is another definition, and maybe the beginning of a theorem. Okay, a theorem or 2, just to see that theorems are still possible in ring theory. It's not just a bunch of definitions. Okay, good. All right, so what is an ideal? Part 1. All right. Okay. What is an ideal? Okay. Ready? Definition. Okay, so throughout, R is a commutative ring. Okay, that's what I'm gonna do. Okay, R is a commutative ring. Okay. So, definition. An ideal is a subset, often denoted by I for ideal. Such that, okay, 2 things. 1, I is a subgroup under addition. So, A in I, B in I implies A minus B. That's a very quick way to say what it means. Okay, subgroup. All right, so there you go. Closed under addition and taking negatives. Okay. 2. This is a weird one. This is a new kind of thing. Okay, this is slightly different than what you're used to. 2. I is closed under arbitrary outside multiplication. Or let me say it a different way. It's closed under multiplication by elements of the ring R. Here's that statement. For any element in the ideal and for any element in the ring, R times A is again inside the ideal. It's closed not just among, so in particular, look at this. Any two elements in the ideal, when you multiply them, you again get an element in the ideal, but there's more. There's more to it than that. You need arbitrary outside multiplication. Okay? And I contains at least 0. But yeah, a subgroup. Yeah. Subgroup. Okay, so next. So let me show you some examples. Some very early simple examples. Simplest examples. Okay, so 1. 2z is an ideal. All even integers. Okay, so 1 is obvious. Condition 1 is obvious. Condition 2. An even number times any integer is again even. Okay? Example 2. 3z. 1. Obvious. That's a subgroup. It's the cyclic subgroup generated by 3. So 1 is obvious. Okay, 2. Any multiple, if you take a multiple of 3 and you multiply it by anything, you get, you carry the 9, do your multiplication table, you get another multiple of 3. All right, that's another example. Great. Let's do another one. Example 2. Example 3. Okay. I'm gonna call it, what should I call it? Let's call it, I. It's the set of polynomials which have no constant term. Okay? And I think of this as, let's say, in the ring of polynomials, one variable with coefficients in rational numbers. Okay? So the ideal here is the set of polynomials that have a 0 in the constant term. So, e.g., 1/2 t squared minus 3t and I. 4t plus 9 minus 1/3 t cubed is not in I. So on and so forth. Okay? Check condition 1. Is this a subgroup under addition? Yes. Take any two of these polynomials, add them, and you won't ever magically get a constant term. Okay, so closed under condition 1, yes. Condition 2, take any polynomial with 0 constant term. Okay? And multiply it by arbitrary. Now here's a secret. When you multiply in a polynomial ring, here's a secret. When you're using polynomial rings as an example, focus on the degrees. Focus on the concept of degree. The powers of t that will show up. You have this concept of the power of t to focus on, the degree. And if you look at a polynomial that has 0 constant term and you multiply by any polynomial, the only way a constant term emerges is if when the two constants multiply, because any other multiplication will have a higher power of t involved. So when you multiply by arbitrary polynomial, one which has 0 constant term, you still get a 0 constant term. This is an ideal. Is the power of t greater than that of arbitrary coffee? This person is right at home here. This is the type of class we conduct around here. Fantastic. That's right, Kappa, you have a rival. You have a rival. Yeah. Good. All right. So, what a weird definition. What a weird definition. Weird definition. Where does it come from? Answer 1. And this will look familiar. This will be familiar. This will be familiar. Answer 1. The set of all ideals all possible ideals in every single example ring. This is the same as the set of all kernels. Just like in group theory, the normal subgroups, you can see it, you can have, they have their own independent definition. Oh, it's some subgroup in preserved under arbitrary conjugation. Oh, gee, wow, wonderful. Why is that interesting? Well, another way to think about a normal subgroup is just, it's some kernel. under some kind of homomorphism. And the kernels measure the ability to shrink the ring. Kernels measured, or back then, the group. The ability to shrink the group. The collapsibility. The non-injectivity of a homomorphism is measured by a kernel. Okay, so kernels are natural. Ideals are just turn out to be exactly the type of thing that kernels are. Remember last class I emphasized kernels are not rings. Kernels are not subrings. Kernels are subsets which enjoy some funny pair of conditions. And it turns out these two conditions characterize being a kernel. We'll see that one day. We'll see that soon, this week. All right, because the second thing, the second answer, ideals are the things that you can take quotients by. And notice, ideals are the things you can quotient by to get a ring again. Okay, let me say this. Let me just point out that this answer is parallel. Normal subgroups are those things that you can quotient by to get a group again. The same exact story justifies the two conditions that are in the definition of an ideal. The ideals are exactly the sub-chunks of a ring that will allow us to quotient and produce a new ring again. Okay? But is it the kernel of someone? Yes, and every ideal is a kernel of something. All right? Oh, the total ring is an ideal. Yes. Okay, let's address that. By the way, R is an ideal. And if you ever want to talk about an ideal which is not this one, you use the adjective. So this is just vocabulary. You use the adjective proper ideal. An ideal that's not equal to the whole ring. Okay, so yes. No. Kappa, the zero map, the map to the zero ring is a ring homomorphism. No. It's not that I consider it as a homomorphism. Check the definition of homomorphism. Does the element 1 go to 1? Yes, it does. Because 1 is 0. So it's not like I separately considered this a homomorphism after our initial definitions. No. This is a ring homomorphism, not as a convention or anything beyond the things we've already assumed. Okay, great. This is a ring. not a rung. Not just. 1 is 0, but 1 exists. There is something that plays the role of a 1, namely 0. In that ring. Only in that ring, though. Okay, good. Next. Oh, hello, Joshua. Okay, so where do ideals come up? They come up in the discussion of trying to construct quotient rings. They are exactly the objects that we'll be able to take quotient by. Okay? And in these examples, these first examples, the quotient object, the quotient ring, will be z mod 2z or z mod 3z in this one. Okay? In this one, we'll talk about it. The quotient will actually be Q, the field Q, for this example. Okay, great. Okay, so that's my first Y. They are the things that we will be able to quotient by. All right. Last thing I want to say about ideals in general is when you're working with a non-commutative ring, you will see things like left ideal or right ideal or two-sided ideal. You'll see phrases like that, class. Now, what this means, when you see left and right and two-sided, they're simply saying that it's condition 2. It's always about condition 2. They're saying that in condition 2, the subset is closed under arbitrary multiplication on the left side, which is how I wrote this. But in a commutative ring, doesn't matter. Okay, what is a right ideal? It's something that's closed under arbitrary multiplication by elements on the right side. And two-sided means it's closed under multiplication from both sides. Okay? So you'll start seeing that those adjectives. Those adjectives are not relevant to us because we're going to stay commutative in this semester and especially all of next semester. Okay, great. Okay, and non-commutative ring theory is much more challenging, much more difficult than commutative ring theory. Okay, great. So now I'm going to show you part 2. Here is a massive recipe for producing ideals. Okay? It's a wonderful recipe. You should think of it as analogous to cyclic subgroup. That was a massive recipe for producing a subgroup quickly when you have a single element. Okay, here are the 2 steps. Step 1. Choose an element. Okay? Step 2. Write this down. Write down this set. It's the set of all multiples of that element. Notice that, so now you see you got this set. We give a name to this. We write this as parentheses A. Okay, that's how we write that. All multiples of A. That's what parentheses A means. Parentheses A is an ideal. This is interesting. So notice the idea of just referring to all multiples of a given element, that sounds kind of important. But if you ask, what kind of an object is that set? All multiples of a given element. That's an ideal. It's not just that it's closed under addition, that we're going to check that, but it's also closed under arbitrary outside multiplication. And these first two examples, in fact, all of them, these first two examples, this one is a principal ideal. Oh, is a parentheses ideal. We don't have the word yet. It's this, 2. This is 3, parentheses. This is t. If you think about it, what does it mean for a polynomial to have 0 constant term? It means that it's a multiple of t. It's t times some polynomial. And conversely, t times any polynomial will have no constant term. So this is also in this family of examples. All 3 of the examples I've shown you are of that type. Okay, so this recipe is pretty big, huge recipe. I'm not going to verify this is an ideal. Verify. Condition 1. You take two elements and subtract them. Take 2 elements and subtract them. Is it again a multiple of A? Well, you can see this by the distributive law. It's a multiple of A. Great. Oh. Condition 2. Suppose suppose you pick an element inside this thing. And suppose B is an arbitrary element. Then B times RA is, by associativity, which is a multiple of A. So arbitrary multiplication keeps this set within itself. Okay? So the principle... Oh, there's a word for this type of ideal. Ideals of the form all multiples of a given element are called principal ideals. They are, in a sense, the simplest... they are the simplest kind of ideal that you can construct. Pick an element and take all multiples of it. All right? That's the... Okay, that's the analog of, like, cyclic subgroup. Okay, but I want to emphasize something. I do want to emphasize something. So let me do an example. Maybe this example is pointless. So this is either going to be a terrible example or it'll illustrate something, some idea, or fix some confusion. So here's some bad example. Let's take, for example, polynomials, integer coefficients. And what I want to look at is the following subset. I want to look at the following subset. Maybe I'll call it L. No, sorry. This is not the example. Sorry. That, okay? Look at that subset. That subset, this subset is the cyclic subgroup generated by T. Right? You take T, do the group law with it a bunch of times, you get 2T, 3T, 4T, 5T, negative T, 0. So this subset is a cyclic subgroup of the underlying abelian group in this ring. Okay? But this is not the ideal generated, is not the principal ideal T. But this is not the principal ideal generated by T. The principal ideal generated by T is much bigger. T is way bigger. So when I said principal ideal is analogous to cyclic subgroup generated by an element, it's not equal, okay? So here's the cyclic subgroup generated by T. It's called L. But the principal ideal T is way bigger because it contains all kinds of crazy new stuff. Like T squared is in here. T cubed plus 4T is in here. See, because this is T squared plus 4 times T. Multiple of T. So when I say, so that analogy is not exact, but it's similar in the sense that you start with one element and you grow an ideal from it. All multiples of that element. Okay, so great. These are the simplest kinds of ideals that you could ever create. And now we're gonna switch to a theorem. So we're gonna try to state a theorem. Some rings are simpler than others. And the measurement of how simple a ring is takes some time. But one way that we measure the simplicity of a ring is in the simplicity of specifying ideals in the ring. Okay, so here's a definition. So rings will have all kinds of adjectives one day. Oh, this ring is this kind of ring because it has this feature. This ring is another adjective. Okay, so this is the first possibly interesting qualifier or adjective that specifies or that points to the simplicity of the ring. So here's the definition. A ring R is a principal ideal domain if every ideal in R is principal. In other words, principal ideal domains are the simplest rings from the ideal theoretic point of view. All right? It's the simplest kind of ring from the perspective of creating ideals. And why do we care about ideals?
because ideals are opportunities for quotients, as we will see next class. Okay, so we give a name to the simplest kind of rings based on how the ideals look in them. And now the theorem. Maybe you did it in 3613? I did. When I taught 3613, I taught this. Theorem. Z is a principal ideal domain. Oh, does R have to be an integral domain? Actually, I wonder if that's true. I mean, you can define it. You can always define this. I mean, but when you write domain, I don't know if that's a convention. I should look that up. We're in convention territory. But the concept of a ring having only principal ideals doesn't refer to whether it's integral domain or not. However, maybe I'm not supposed to use domain there. Maybe I'm supposed to use principal ideal ring. Who knows? Let me look it up. Principal ideal domain. Maybe the word domain is oh yeah. Principal rings. Ah, Bourbaki. Okay. Yeah, so domain, when we say principal ideal domain, it's assumed to be an integral domain, which we don't have to. So maybe I should fix that. So the word domain seems to be enforcing one more condition. But then what's the definition? What's the general definition? Oh, principal rings. Okay. So two-part definition. A ring is a principal ideal domain if R is integral and every ideal in R is principal. Okay, part two. It's called, now I have to remember this. Part two, it's called a principal ring. Principal ideal ring. Principal ideal ring. If we just drop the integral domain requirement. Yeah, I'm just going off of what Wikipedia says. Good. Okay, great. Okay, so class, whenever you see domain, this is what I learned. Whenever you see domain in a vocabulary word, probably for some reason, they're probably assuming integral domain. In this case, the concept that every ideal is principal doesn't refer to any kind of structure in the ring beyond that. So principal ideal ring is much more general situation, and then domain adds in the condition of being integral domain. Great. In any case, the theorem still stands. Z is a principal ideal domain because Z is an integral domain. Z is integral. Okay, so Z is a principal ideal domain. That's a theorem you learn early on. So how does the proof go? Okay, The proof is has a name. It's called what is it? The proof has the technique is called division with remainder. What is it called? Division algorithm. Division algorithm. Or division with remainder. Okay? Division algorithm or division with remainder. Euclidean algorithm. Okay, what? No. Long division. Long division. It's called long division. All right. So here's let's write out the first steps. Let's write out the first steps. Suppose I is an ideal. Okay? And for simplicity and assume I is not the zero ideal. After all, the zero ideal is a principal ideal. So we can assume it's not that. The step one, first step. Oh, there's, yeah, division algorithm plus well ordering principle. These things have names. The next move is well ordering principle. By the well ordering principle, there is a smallest positive element. Thank you, Kappa. Suppose you're not looking at the zero ideal, which is already principal. Zero ideal is always principal. There is a smallest positive number that's in the ideal. Okay. Now, suppose B is any other element. Okay? B is an integer, by the way. B is an integer. Right. So here's the division algorithm. Right. B equals A times Q plus R, where R is in 0, 1, up to A minus 1. Yes? You see that? This is the point of this is the whole theorem right here. Write that. Okay. Since B is in I and A is in I, then Q times A is in I. Arbitrary multiplication. Property 2. And therefore, B minus AQ is in I. Closed under plus minus. And so, R is in I. But hold on. R is a number from 0 to a minus 1. And a is the smallest positive number that's in I. So r has to be 0. Since a is least positive element in I, we get that r equals 0. i.e., b is a times q for some q. Done. Every element in I is a multiple of A. All right? And by the way, this proof actually tells you how to find the generator, or a generator, an element whose parentheses is a given ideal. You kind of look for the smallest positive element in that ideal. Okay, I know class is over, but I just want to go through this proof and point out some very special things about Z that made it tick. That's what you should always look for in ring theory. What extra structure in this ring made this statement possible? Okay, so the first thing was this idea of smallest positive element. Now, if you look at an arbitrary ring, there is no obvious notion of elements being bigger or less than other elements. That's some added thing that we have available with the integers. So putting the elements in a row and kind of saying one is bigger than the other, measurement, some kind of measurement device on the elements, that was used critically here. Secondly, you had some algorithm or procedure that took two elements and did division with remainder. But what was key was that you can ensure that the remainder is smaller than the thing you're trying to divide by. The remainder part is smaller than the thing you're dividing by. That was key. That was key as the second part of the argument. And what does smaller mean? Smaller in the sense of whatever happened in step 1. Smaller in that sense. So what was critical in this proof was that Z has a notion of size. The integers have a notion of bigger than or less than. And we'll see that some rings have such a thing, and they are quite often principal ideal domains. And other rings, they don't have such a structure, and they're typically not principal ideal domains. And so next time, or maybe the time after that, I'll do the same argument The same argument shows that theorem. Suppose F is a field. Then the polynomial ring is a principal ideal domain. Okay, we'll do the same argument. Something about polynomials in one variable. There's some structure or measurement you can make, which is analogous to the measurement of the size of an integer, the positive and negativeness of an integer. That's cool. We're going to see the same theorem, but in a different ring. And that's next time. Possibly the last third of next time. Okay, great. So ideals, principal ideals, theorem. That's what we covered today. Tomorrow, Why ideals? How to quotient by an ideal. Examples of quotient rings. And then back to this theorem for that polynomial rings in one variable are principal ideal domains. Coefficients have to be in a field. Okay, so that's next time. That's Wednesday. Okay, let me look at this. Shaquille Oatmeal, howdy. How's it going? You want me to juggle? Fine, I'll juggle. I must be a subgroup of Z, right? Exactly. 100%. 100%. And we use that RDL. If you saw in the proof, used it right here. And this is, both parts were used. This is condition 2. This is condition 1. What's the name of the theorem that says ideals are kernels of ring homomorphisms? It's called the first isomorphism theorem for rings. It's the same thing as, it's the same theorem as normal subgroups are quotients. I mean, normal subgroups are kernels of group homomorphisms. It's the same thing. It's the same difficulty, the same role that's being played. Okay, let's do credits. Roll credits. Then I have to learn. What am I teaching? Oh yes, power series. Pro was instrumental today. Wait, why? Teacher's pet. Okay, who else was here? RDL is here. RDL. Coming to class like a boss. Kappa. Can I say among friends that an ideal is just a commutative associative ring? An ideal is a rung in general. A rung, rung without the one. But so I would say no. I would say that is missing. So the interest of an ideal is how it sits in the ambient ring. It's always an ideal of what? When someone says ideal, the context is within an ambient ring. If they just say, I have an ideal, and that's it, what they're saying isn't really making any sense. What do you mean? What do you mean you got an ideal? Where, in what? What's your ambient ring? It's important to remember that. Exactly, RB. Yeah, ideal is a relative notion. It's kind of a relative notion. Like normal subgroup. If someone just says, hey, check out this normal subgroup. So, in what? What's your big group? You can't just come here and tell me, look at this. Your first sentence can't be, hey, check out this normal subgroup. It needs to be, hey, take this group right here, and now check out this normal subgroup in it. Same way, ideal has to be inside of some ambient ring. Wonderful. Great questions. Okay. Vixen, late arrival. Absolutely, you made it. Vixen. Party. Okay. Who else is here? Gath. Oh, Gath was. Oh, my bad. Gath. Is that better, Geth? Is that everything settled? AC. AC. Algebra master. Oh. Dallas. New friend. Median. Watch out. Shaquille Oatmeal. You're making it just for the name, okay? Name. That's the only reason you're making it, okay? Mm-hmm. Yeah, Kappa. The tides are changing. Triple threat right here. Dallas with the triple threat. Okay, I know people redeem stuff, so here you go. What did people redeem? They wanted a twisted cubic. That looks like a parabola, but that's because under certain projections, you lose something. Okay. All right. What else happened? Juggling, recorder, shungite from Fluffy Potato. Twitch streamer. Karaoke master. Wants some shungite. Probably got a new iPhone. 5G. All right. Recorder. Juggle. I'll just do it simultaneously. Unless Dark Caps. Do you want an actual song, or do you want the one that I play when I juggle? Which has it's mostly rhythm, really. It's a very rhythmic song. Okay, good. All right. It's a rhythmic song, okay? Although with music these days, it probably will pass as a song. Okay. Oh. Okay, 2 for 1, done. Done with requests. UB Math Prof. UB Math Prof comes in right at the end. All right, here we go. Things are getting spicy. We've got a competitor in the audience. Go check him out. Teaching Calc 3 right now. Calc 3. Beautifully, with amazing illustrations and everything. Okay. All right. Okay. Did I get everyone? Who here feels that I didn't give them their attention? Is there anyone? Oh, wait, where's Arbitrary? Arbitrary is the ancient friend. Hey, Arby. Aren't you like... Oh, you were here. Okay, BPS. Tech Master. Okay, good. Wait, Kappa. Right. Right. Yes. Okay. Kappa. The quotient ring is there, but it's not just because there's a quotient ring doesn't mean that it's any one of the rings that you are biased towards wanting to see in the world. Kappa. The amount of objects in mathematics is typically far beyond the list that you wish everything fit into. So that ring exists, Kappa. Is it nice in any sense? Does it have some beautiful structure that you're used to for other examples? Probably not. But it's there. Just because it's confusing as an object doesn't mean it's not there. Okay, Arbitrary. Hey, Arbitrary. How long have you been around? I mean, here. Are you from like March or something? Like March, April, May or something? For some reason I remember you being here like way early. Yeah, it's from May, exactly. Exactly. That's crazy. Okay. Okay. So here we go, credits. Pro. RDL, Cap. RDL, who else was here, by the way? I don't know who else was here. All my students. Chapters. Vixen, late. Kappa, jokes. Dallas, better jokes. Possibly. I don't know. Arbitrary, ancient friend. Shaq, good name. Fluffy, streamer. UB math prof. Insane. Great professor at UB. And all the mods here. Awesome. All right. Now I gotta learn about what's the topic for today. What does WebAssign say I need to teach? Power series. That's a fun topic. Oh, sorry, Gath, you're right. These are... Wow, my PayPal is just... Wow, exploding. Now that I did that. That's crazy. Thank you, Gath. Thank you. Isn't that how business works? That's business, right? Vixen, you need more Veronese surfaces in your life? Hopefully, if I stay on track, Veronese surface will happen next week. Thursday or Saturday, I don't know. Next week. Veronese surface. Not this week. Next week. Okay, good. Yeah, week from Thursday, if I stay on track. So you got to wake up early? I don't know where you are, Vixen. I don't know where you are, but But you do need to wake up to watch it. That much I'm sure of. It's gonna be like in the afternoon for me. Like 1 or 2 p.m. Central Time. I don't know where you are, Vixen, so. Wait, Vixen, you're a sub? Oh. Fun. I did not know that. Awesome. Oh, you're on Earth? Okay, that's good. That helps. That helps. Okay. Yeah, what's up? What's up? Oh no. How does that happen again? How does that happen again? Kappa's not here anymore, but luckily. Yeah, I know. I was gonna try to draw legs, but I actually don't know how to draw legs. That's pretty good. Not bad. Okay, let's get out of here. This is getting far too degenerate. All right. Okay, I'm just gonna start waving thing. You know how the politicians do it? Have you noticed this, folks? They'll just like wave and then they'll just like point. I bet you there's no one there. Just stupid. That's so stupid.